this lecture, I'm going to talk about different classes of chemical reactions. Now, a lot of these reactions we've already talked about this semester, but we didn't put them into categories, and this is what we're going to do. Before I begin, I just want to review that in chemical equations, we sometimes see symbols after the chemical formula in parentheses that so either S, L, G, or AQ. So S stands for solid, L for liquid, G for gas, and AQ is aqueous, which means dissolved in water. Now, we don't always show these. Sometimes it's important and sometimes it's not. But when we're classifying chemical reactions, one thing that we're looking at is whether a change in state occurs, or whether a change from aqueous to solid, for example, occurs. So we do often show this information when we want to find out what kind of reaction is. So the first class of chemical reaction we're going to talk about is a solubility reaction. And this is a reaction in which an ionic compound dissolves in water. This is something that you've probably observed many times. For example, if you take sodium chloride or table salt and mix it with water, you solubilize the sodium chloride to form Na plus and Cl minus ions. So this is a solubility reaction. And I should point out that not all ionic compounds dissolve. For example, silver chloride, HCl, is a solid in water. It will not dissolve in water. Your textbook indicates that you should memorize these, but I think it's kind of a waste of time, so I'm not going to ask you to do that. Just recognize that some ionic compounds dissolve and others don't. So we have the solubilization reaction. A precipitation reaction is the opposite, where we have something that it's basically things mixed together in solution and form something that's insoluble. So let's take a look at how this reaction might happen. For example, if we have potassium iodide, or Ki, and it's a solid, and we mix it with water, it forms potassium ions and iodine ions. It is soluble. And then lead nitrate is also soluble if we mix it with water, so we'll end up with lead and nitrate ions. So both salts are soluble. Now, what if we take 2 beakers of these and mix them together? When we do this, we end up with all of these ions together, and it turns out that lead iodide is not soluble. So when the lead ions happen to meet the iodine ions, they're going to react, and they're going to form a solid that will precipitate out of solution. So we indicate this with an S, and when you have all aqueous on the reactant side, and you have a solid on the product side, this is a precipitation reaction. All right, so again, aqueous means the salt is dissolved. So when we look at this, if we see KNO3 aqueous, or potassium nitrate AQ, what it means is K plus aqueous and NO3 aqueous. Now, we could also write the equation, so the solubilization or the precipitation reaction, like this. So we could write Ki aqueous, and that means K plus and I minus, and PbNO3 2 aqueous, so that would mean Pb2 plus and NO3 minus, and then lead iodide solid, and then KNO3 aqueous. So when we look at this, even though we don't show the ions, the aqueous indicates that they exist as ions and not joined together. So at least that's the way they are for now. Like if we did evaporate all the water, we would end up with potassium iodide solid, and with potassium nitrate solid. Another important type of reaction is an acid-base neutralization reaction. In this kind of reaction, when you mix together an acid and a base, and you end up with water. Take, for example, hydrochloric acid, or HCl. It's a strong acid, and when a strong acid dissociates completely in water to form H plus and Cl minus ions, and this is something you'll learn in more detail if you take Chem 102, and sodium hydroxide is a base that dissociates into Na plus and OH minus ions, and again, it's a strong base, so it dissociates completely in solution. So what happens is when we have HCl and NaOH aqueous, remember we're going to have those ions in solution, and the H and the OH are going to react to form H2O, and the Na plus and Cl minus, that's simply sodium chloride, that is soluble, so that's going to remain in solution. So water is a product of this reaction, and then we also have a solubilized salt. The next type of reaction I'm going to talk about, oxidation-reduction reactions, is the most complex. In an oxidation-reduction reaction, which is often just called a redox reaction, electrons are transferred from one element to another. So this happens, for example, when ionic bonds are formed. It's in the case of formation of sodium chloride, a electron is transferred from the sodium to the chlorine atom. And when this happens, we say that the chlorine atom is reduced because it's got a more negative charge than it did before, or it's got more negative charges around it. More electrons, so it's reduced. And the sodium atom is said to be oxidized. So oxidized means that it has a more positive charge. So basically, redox reactions happen when you have two different elements, and one of them wants the electrons more than the other. So in the case of sodium chloride, oxidant chlorine is a nonmetal that wants the electron very much. Sodium is a metal that doesn't want it, so the electron gets transferred from the sodium to the chlorine. Now, it may seem obvious that ionic compounds, when they form, they undergo redox reactions, or reactions when an electron is transferred, because it's very obvious to see this, especially if you draw the Lewis-Deck electron diagrams of this process. However, even molecules, which are formed between nonmetals, where electrons are shared, can undergo redox reactions. What happens when a molecule undergoes a redox reaction is that atoms undergo partial oxidation and partial reduction. And the reason this occurs is because of the difference in electronegativity of different nonmetals. Remember that hydrogen has the lowest electronegativity of any nonmetal, of 2.1. Carbon has a somewhat higher electronegativity of 2.5. And oxygen has a very high electronegativity of 3.5, which means it wants electrons a lot. In other words, you can think of oxygen as an electron bully. When it gets near to another atom, it's going to try to steal its electrons. Now, like all bullies, oxygen would rather fight over electrons with a weaker atom. So in the oxygen molecule, on in the reactant side of this equation, we have two oxygens that are fighting over electrons. They're both have an equal strength pull on the electrons, so neither one can win. And although this is a stable molecule, it's not an incredibly happy molecule. The oxygen atoms would really rather to have a tighter pull on electrons. And it turns out they can do this in water. So remember, oxygen's a bully, and hydrogen, which has an electronegativity of 2.1, is a weakling. So oxygen can pull the electrons away from hydrogen pretty well. Now this is still considered to be a molecule where electrons are shared, but it's an unequal sharing. the oxygen atoms have the electrons a lot more. So when we look at these two molecules, the oxygen atom is much happier in a water molecule than it is in a dioxygen molecule. And another way of looking at that is that energy is released when oxygen is converted into water. And the reason this is because electrons essentially exist in a lower energy state when they're pulled tight into the electronegative nucleus of the oxygen atom. So the electrons are very close in to the positively charged oxygen in water. They're less pulled in when they're in this tug of war between two oxygen atoms. And this is, like I said, it's a pretty complex process, but it's also incredibly important in biology, which is why I'm going into detail on this. So this basically, if you look at at this diagram on the left, which is from a biology text, it kind of shows the sharing of electrons. So on the left here, on the reactant side, we have methane, which is an organic molecule, and the electrons are shared more or less equally between carbon and each hydrogen, and they're also shared more or less equally between the two oxygens in the oxygen atom. Now, if we look at the right, like I already mentioned, the electrons are pulled in tighter to the oxygen and to the hydrogens in water. So this is a more favorable way for the electrons to be. They're in essentially lower energy state. And they're also in a lower energy state in carbon dioxide, because even though carbon dioxide is nonpolar, it's got an equal balance of charges. However, the electrons are closer to the electronegative oxygen nucleus, which is more favorable for them. So both of these, the carbon dioxide and water, are both in a lower energy state than methane and oxygen. So energy is released, and methane is, again, the molecule, the primary ingredient in natural gas. And when it combusts, it releases energy, and this is the reason because electrons end up in a more favorable electron configuration. So in this reaction, just like in the one for the ionic compound, we have a reducing agent and an oxidizing agent. So methane is the reducing agent because it basically, reducing agent donates electrons, and in the case of organic compounds, it also tends to donate hydrogen atoms because the hydrogen atoms have a weak pull on electrons. So when they're donated, the electrons can more tightly link to the oxidizing agent, which is typically oxygen. And so this is why we have the word oxidizing agent, because oxygen is the most important oxidizing agent for all biology reactions and also many reactions in a chemistry laboratory. And it was also the first one understood and studied, so that's why we have this word oxidizing agent. So when you have oxygen, what it tends to do is pull electrons and hydrogen away from other atoms.